needs this to be a day of Friday, we can change it to a day of Friday. So we'll be
Tiến tốt chơi với thầy đi. Bộ trưởng bộ ăn chơi.
all right, so I just want to look at some performance measures. And then maybe for simplicity, let's do it not with so many assets, but with few. Okay? For example, let's say we play with Apple, Amazon, and then we estimate rates, different rates. Right? Just two, not 100. Because then we no problem. So then we give you a little bit more work, essentially, to do it. So we do it, well, it's slightly different. So that's sort of what I want. Well, I mean, for example, let's say, well, as I just mentioned, so let me take those. I mean, the data I will take again. So here. Right, so that is, so I mean, up to this return, when I was taking the assets, so we take them from, just enjoy your food. So that is what I will take. And just will do few assets. Alright. So, well, I mean, what did I do in the very beginning? So I did with Apple and Amazon, right? Two assets. So that is these two, so Amazon and Apple. Alright. So assets I will make small for the specific rating scheme that we have. Alright. So, well, in general, then you do it with more assets, like all of maybe components. I mean, I just focus on components of this amplifier. You can take in there. You can take gold. You can take whatever. So, all of the assets you put together and then start to do analysis. So, but you don't need to just focus on those. So in general, you may go to equities, goods, so on and so forth. Right? So that's sort of not only this. So when it comes to investing. But as I said, so here I just want to focus on what a smaller, maybe scale problem, right? And so that I could focus on the performance. So that's the same thing as before, as we did in the very beginning, together with just Amazon and Apple. Right? Now let's say we have optimal weights, right? So let's say optimal weights, well, I mean, there could be different versions. For example, let's say we did it, and then with Amazon came 30% and 70%. These were the optimal weights that we got with the historical data. But let's say we also tweak it a little bit, say a bit more in Amazon, a bit less in Apple. So let's call this optimal weight 2. Right? So these are two weights, two different portfolios, and then we want to compare it. Right? So, so what we need essentially is the returns of the portfolio, right? So first time, all right. Well, let's say in the beginning of 2024, we start with this portfolio rate. All right. So let's say it was well, the beginning of the sample, which was the 1st of January or sometime in 2014. Right? And then we say, all right, so we invest 30% in Amazon, 70% in Apple. Or 40% in that, 60%. So already two different portfolios. And then we keep it for the whole sample till now, so 10 years daily. And then we see what is essentially the what happens. All right, so do we get something? Do we earn? Do we lose? And so on and so forth. So that is what we want to do. All right. So let's calculate the weights, all right, or sort of the portfolio returns. So these are the port return. All right, with baking scheme 1. All right, and then we do rest, and then we need the dot product. All right, so that gives you the returns. The return of Amazon times 30% plus returns of Apple times 30%. We add them, and we will have the portfolio return. So if I keep it, then this will be the returns that I have on a daily basis. Right? So that is what we have. Right? So I will just dot product that with the optimal weight same line. Right? So that will be the portfolio returns daily. Right? But then, so I need the cumulative returns. Let's call it cumulative returns 1. And because these are log returns, then I can add them simply. So whatever I earn in the first period plus what I earn in the second period and so on and so forth. That will be added. So if there were percentage changes, then you have to do common cumulative product. Alright? You know. So if there were percentage changes, the returns, you would have said 1 plus return in period 1 times, that will be what we have. So 1 plus the return in period 2 and so on and so forth. That will be cumulative product. Right? When we do log returns, then we simply add them. Okay? And then subtract 1, of course, right? So let's do that. So that will be the port returns, and then here becomes something. So that will be a cumulative, so how much actually do we get? So sort of as time passes. So that is what we have. Okay. Right. And then we also need, so if I want to calculate the Sharpe ratio, right, then I also need to calculate standard deviation. The Sharpe ratio was the ratio of the risk-adjusted returns were adjusted with the standard deviation. Well, how would you estimate the variance then? Well, okay. So let's see. So let's see what do we want to calculate. Alright. Well, here we have no returns at period 1. Alright. And then we have the return in period 2. And so on and so forth. Right? So this one calculated for us the cumulative returns, which is okay. I'm happy with it. So it adds all of the returns. And then I have, after say 1 week, how much did I earn? Sometimes I will lose, sometimes I may earn. So and then over time, if I have more positive than negative, then I will be earning. So that's sort of what it shows when the performance of portfolio in terms of returns across the periods. But then I also need to know sort of what is the volatility of my returns. How much returns do I have every returns of my portfolio, let's call it index equities. These are not the returns of Apple or Amazon, but rather the W1 times the first asset plus W2 times the second. Right? So I need to know how much risk do I have, say, here in T. Then I need sigma. So I need sigma T of the portfolio. Right? So how do I estimate that? Yeah, very good. So we can basically say that this is equal to W1, the variance of the first and here in T, right? Square root, square root, is equal to T squared plus 2 W1 W2 sigma W2. Right? So that becomes the variance. And we estimate this separately, this separately, this separately. All of them are given. Right? And then I go on. Well, this you can get using garbage. And this you can also get using garbage. If I want the covariance, then I can maybe use a multivariate garbage so that I get the free. So that is what we can do. When we have done the methods. Sorry, maybe my question was not so clear. Right? But you are right. Okay? But we could also do differently. Right? So if I'm interested in this, then I can calculate this directly without the formula. Because I have those returns, not individually, but as a portfolio, then I can estimate a gauge on this guy. Not on separately, one by one. I don't care. Right, so what about the W's? Well, maybe one is better, I don't know. But I could alternatively do the estimation of this using a gauge on the returns of the portfolio. Because that is the goal. Right? I could also not do a gauge, I could do a rolling window. Right, so rolling window, that's also not enough. So you remember that we captured a lot of variation in the condition of volatilities, which we can do too. Let's take 22 days, roughly months, as a window, and then we get the rolling window volatility. I will just use the volatilities, which are rolling window, and that will be the portfolio returns, or will be more complicated stuff. I don't know. There will be rolling, right? With the window, which is equal to 20, then I get a standard deviation. Let's just do it so that we make sure that it works. So this is the assets, these are the returns, these are the weights, and these are the portfolio returns, these are the cumulative ones, this is the W, and this is the rolling window. Right? So, rolling window volatility. Let's have a risk-free rate of, say, 0.02. That's generally risk-free rate is very low. Alright? 0.2%. And then now I can calculate the Sharpe ratio. Sharpe ratio. Right? So which will be expected returns minus the risk-free rate divided by the standard deviation. Right? So that's sort of what we can do. Well, I mean, we can also do the mean of rolling window. So rolling window expected return for portfolio 1, and then we get that. Alright, so that's sort of what we have. Now that if I have the Sharpe ratio, then I can say, alright, so I have the rolling window expected stuff minus the risk rate divided by the rolling window volatility remember what did we do? We said that we go in the very beginning of the sample, correct? And then we calculate at the end of the sum, so cumulatively what happens, so how the returns actually behave. And so I wanted to calculate the Sharpe ratio, but sort of react to the movements of the volatility and the return. Because that's the expected return minus the risk-free rate divided by the standard deviation. And that is what I do here. Now I can plot. And I can do the same with the other rates. Alright, so I can redo it with the second rating scheme. Okay. Just maybe do that too. Alright, so I take a copy of all of those lines. And then you do two. Let's do two. So optimal rates 2. Alright. And then you can take a copy of these two lines. And then another short rate. Well, the risk-free rate may also change. If it does, just take it simple. Plug in. In reality, you may actually change this to the actual values. Alright. Now we can plot it. Alright. Well, these two just to see, alright, well, this is Sharpe ratio 2. So that is 1. This is 2. Let's plot. So PLT dot plot of Sharpe ratio 1. Alright. Well, that's just one value, so let's look at it. Sharpe ratio, that's a series. It has a date index, but of course the first 22 are off because the window size was 22, so the first months we don't have any values. And let's add a label. Alright, so the label is with these weights. Alright, so optimal weights, optimal in some sense weights are these. And we also have another one with 40 and 60. Alright. And let's PLT dot plot. And PLT dot show. Well, I mean, they sort of overlap to a great extent. Alright. But some, maybe we should look at the difference. Alright. So it looks like that there is not much of sensitivity with respect to this. Maybe. Alright, so because the blue sometimes seems to be a little bit larger, probably sometimes it's smaller, so we don't really see it on top of each other. Right? They are pretty close. I mean, somehow one of them should be better in terms of, say, returns or maybe volatilities. Right? But it's actually, what I can do is add a little bit more color or sort of dimensions to this plot. And by generating maybe a figure, let's add an axis to it, and that will be a PLT subplots of just 1 by 1. But I want the axis. Alright. So let's have the fixed size. here on the y-axis, then we have the sharp ratio. I want to add another plot, but I want the second y-axis on the right. Right, so that's what I want to do. So I will take 3 of these axes to generate another axis. So axe 2, then I plot the rolling window volatilities for 1. So that is okay. That is the first one. I don't know which is which actually in the previous one. Oh, we have a label. Let's add labels here. 2. That is port 1. And then on the same axis, here, then we can add the 2. Then we put. Let's see how does it look now. I don't know. Oh, this is subplot 6. Right, so the subplot is a different function. No, the colors are ugly. The color is say green. And the color here is blue. ELT.legend. And ELT.green. So that we can compare. And I mean, the volatility seem also not very much. Right, so that's not surprising, but given that the sharp ratios are similar. Alright. But let's maybe instead of volatilities, I will redo these. Alright, so instead of volatilities, I will also add the cumulative part. Maybe in a different graph. Cancel PLT.plot of cumulative returns. Alright, so let the color be blue. Alright, so that is the first one. So label is port 1. Then we have 2. That's the other return. Blue. ELT.legend. ELT.green. Let's just see how they look like. They're pretty similar. Are they really correct? Well, there is probably there is some variation sometimes. Or not, it's 1/2 meter. So that they are different. Well, they are very close to each other. Alright. Right. That's actually so nice. So if I was buying whatever, so in the beginning I lose a little bit, then I go up, then I lose again, and so on and so forth. But the overall trend is really strong. Alright. So if I was buying, well, these are
percentage changes, numbers between 0 and 1. Yeah, right? So the 2.5 means 250%, all right? Which is pretty large. But that's not surprising. This is Apple and Amazon. And they have been on the rise for a long period of time. So if you were buying them long time ago, then you would have earned 250% over the period of 10 years. Maybe it's not so much, but it's somehow interesting. Well, if you change the weights, for example, we look more, sort of more variation in this, so if I had more assets, then things would have changed strongly with respect to the sharp and so on and so forth. And the two, it seems that there are two very risky ones and very similar maybe in the structure, so there is not much of variation.
One so long, precise.
Do you have questions? All right.
Can you calculate the Traynors ratio for these two assets? And plot them.
Alright, so not the cap M, not the sharp ratio, but rather the trainer. And then the trainer, then you just go, and then of course you should do rolling window stuff, because they're very simple and generally good. So here we have the sharp, which is the expected return of the portfolio minus the risk-free rate divided by variance in portfolio, standard deviation. And then this was the estimate, so this the estimate using a rolling window of 22 days. And then this will also be rolling window of 22. That's what we did. For the last 22 days, we took an average, the last 22 days, we estimated the standard deviation. So now let's look at Traynors ratio. Then we do the same, expected value of the returns of the portfolio minus the risk-free rate, and then here we have the capital beta of the portfolio. Alright? So, which means that when you have the returns of the portfolio, you regress that on alpha, market, basically return plus all of the other, if you use a form of French 5, plus the residuals, IT, right? And then here we have beta. Well, you can do this in a rolling window of say W equals 60 days. Then this you can estimate and plug it in. Okay? Then it becomes Traynors. And that's different indeed risk management. Right? Well, which means that we bring the farm of French, run regressions, get betas, plug them in across time, and then plot them. So that will be also allowed. But of course, the higher the Traynors ratio, the better.
Traynor.
can do this as an exercise. Whether I sit down, run regressions, you have the data, you can run OLS, then you can look at it. Let me see, what else can I do? Put this recipe into a different group. Maybe I can take some of their exercise and do for you. I don't find my stuff, I will just talk. Alright. So, well, what I did with you is something you know, because you knew Sharp, and you knew sort of stuff like this. I only deviate from it a little bit. So go away from the classic or textbook examples, so to speak, to open a door for you so that you can think more, so that think of other models. Because this is not the only way that you sort of will go on and then find weights, right? So the weighting is. Well, so what we do here is that, so sort of what we are doing in this stuff, that we have the Sharp ratio and then we have mean one, so maximizing this with respect to the weights. Right? Now, the thing is that, well, let's remove this and what we can do from an exercise. And I will tell you how to implement them, so that's not boring. Well, I mean, when you put together a portfolio, this means that you have some ratings that the final sum. Right? So that's the portfolio weights. Let's say you have the portfolio weights times the covariance matrix times W, then that will be well, if this is a current, then the whole thing will be just a scalar, and then it's the variance of the portfolio. Right? So if I take a square root, then it will be the total risk of the portfolio that we have. For the optimal rates, whatever they are, then you find this as the standard deviation or the risk that we have for the portfolio. Right? Now, well, so this sigma, well, let's call it sigma of W. What type of function is it? If you look at this, this is indeed a homogeneous function of degree 1. So if you make W, if I sort of replace, you understand that, right? So here, sigma P of say lambda W is lambda sigma P of W. So from your economic courses, that is the power of 1, so this is a function which is homogeneous of degree 1. Okay? You understand that, that's not actually a big deal. So sigma of lambda times W becomes lambda sigma W, that's what degree of homogeneity. Alright? So because that's like so, then we could indeed think of this sigma W, right, as, well, let's say we have n assets. Alright, so you can think of it as the summation of n individual standard deviation, sort of. You can think of it like this, because there's homogeneous of everyone. Without going too much in the functional analysis, where each of the sigma i's is the risk contribution of each asset. Right, so, well, so to speak, let's say if I have Amazon and Apple, then they have a certain contribution to the total risk that you have. Right? So now, one may actually contribute more, one may contribute less. So one has more effect, more basically influence on your portfolio compared to the other. And so that's sort of what we generally have. Right? So that's sort of the risk is not balanced. Right? So risk is not uniformly distributed across different assets. Right? Some people actually started thinking of this, and then they thought, maybe this is not a good idea. Right? Maybe we can make the risk contribution balanced. Right? So that they have the same. Yeah, so they have the same indeed risk contribution for each asset. So Amazon has the same risk contribution as American Airlines, the same one. Right? So that actually generates a different way of choosing weights. So to speak, you choose the weights so that the risk contribution for each individual asset is the same across all of them. Right? So what is then the risk contribution? So the risk contribution of each of these assets is indeed, well, you have to now see what is this sigma W. And sigma W is, just to get it right, now we can do this again. So this sigma, this doesn't right. Sigma W, alright, so when we use the individual risk contribution to each of assets, and then sort of they are added together, so that we have that. That is the weight, WI, that we get, times the derivative of sigma TW with respect to W. Well, that's sort of, the change that we have in here. So that's the derivative with respect to W multiplied by W. So how much this infinitesimally changes when you change WI, the ith component, multiplied by W. So that is something that, well, if you, so given the form of this function, if you do this and plug it in the summation, and then do a little bit of calculus, then you get back to the function which we have it as a square root. So that's sort of what happens. Well, we don't know find them. Alright, so what we have, so I'm actually sort of playing around with this. First is that this is a function which is homogeneous of degree 1. And because of that, then this function can be written like so. Alright? So that's sort of more or less like, it's not a linear function, but that's a homogeneous function of degree 1. Right? Well, what it means maybe in simple words, now let's say if I have f of x is equal to x, right? Then f of x1 plus x2 is the same as f of x1 plus f of x2. Because that's homogeneous also of degree 1. Right? So that is something you know, somehow so clear to see. And here is a little bit more, that's non-linear function. In any case, that's homogeneous of degree 1. Because of this, then you can write that as these components, where each of those components is a derivative with respect to each of the values. Alright? Clear? Well, let's look at this function. Alright? So f of x, just so that you see the point. Alright? So this is like x1 plus x2, because f of x is the same as x. Alright? Now let's take a derivative of this with respect to x. That is 1. Alright? So times x1 becomes x1. Alright? So this is like x1 times the derivative of f with respect to the whole function with respect to x1 plus x2 times the derivative of this function with respect to x2. This is x1 plus x2. Right? Do you agree? Okay. But I mean, that is what I wrote there. Right? So I wrote the function because that's something, it's very important. And this is homogeneous of degree 1. It is like that. That's very simple because that's really you see it in front of you. So I'm generalizing this. I'm saying, okay, we have homogeneous of degree 1 quantity. And W1 times the derivative plus W times the derivative. And if I put them together, then I get back to what I was. Because of, you can show it. Okay? It's actually not a big deal. Okay? Well, I mean, let's calculate the derivative. Alright, so if you calculate the derivative of this with respect to the ith component, alright, well, so that's some function to the power of 1/2. Right, so that will be some function, but this is to the power. So then I have to see where W1 is. Alright, and W1 is one of those components, but it will be showing up in the row. Because someone might multiply by everything. Right. So if you take the derivative, keeping this in mind, then this will become WI. So times, well, that's to the power of 1/2, then the function itself becomes like. So let's say if I have f of u equals u squared and u 1/2, then what is the derivative? Then it is f prime of u 1/2 u to the power of -1, right? So square root in the denominator shows up, which is here. So that's the square root, which is square root of W1 prime W. That shows up in the denominator. And then I have a numerator. The numerator will be sigma W of the ith row. That's sort of what the ith component of this sigma times W. Because the ith component of this is basically, when you look at me as if I am talking about let me do another numericals. Okay. Well, let's say we have W1, W2, right, multiplied by 1, 2, 2, and 3. Times W1, W2, and all of it to the power of 1/2. Okay? You have to run. Right? So let's do the multiplication. So then let's multiply this with that. Then it will be, that will be equal to, so 1 times W1 squared plus twice W1, W2. Right, so now W2 comes in, plus twice W2 squared. Now what is this? Twice W1, 2 W1, 5 W2. So this is W1 squared. W1 times W2. And then 5 W2 squared. Yes, nice call. So, yeah, that will really some of the change. So that's how it is. Let's take, now this is go to the power of 1 half. And this is also to the power of 1 half. Alright? Let's take now the derivative of these with respect to W1. And that's actually a nice technique when it comes to portfolio optimization. I feel like that now that I'm here, I can tell you it will be a very easy way. So let's look at the derivative of this whole guy with respect to W1. Alright, so then here we have 2 times W1. Okay, there's 2 W1, W2, and W1, W2 twice. It is 2 times 2 W1, W1. Alright, so that's what we have here. And that is 0. W2, sorry. Right? And then divided by the whole thing, which is the square root of W prime sigma W. And this is sigma, this is W, this is. And so just write it like this. And then because that's to the power of 1 half, and here we have the 2. Yeah. Okay. So then this is like 2 cancel, and there is W1 here, plus 2 W2. And then divided by W prime sigma W. Okay. Now let's look at this. Alright. So this is 1 W1 plus 2 W2. Yeah. So that's the first element, and this is what? This is sigma W. Right? Well, this is W prime times sigma W, but that is what I'm interested in. Okay. And that is the first element of this. Now let's go look at this. Right, so this is W, and that's the derivative. The ith element of this divided by whatever it was. And so that is the risk component, risk introduction of asset I. WI times this. Do you agree? So then we have all the risk components, or risk contributions. Sigma I. This is the functional form. Alright. So now if I want this sort of to, well, so that they are all the same, I want these risk contributions to be all the same. Right? So across all of the assets, then what I can do is just to make them all the same. Alright, to say that sigma I W is equal to sigma J W for all I and J. Alright. So then for W1, then I for I equal 1, then there is some expression. For I equal 2, then there is some expression. And we find some system of equations in unknown variables. which I can go find. Right? So there is some method in portfolio selection. We will take a red pen and write it on the board. This is called risk area. Okay, so it makes the risks, well, risk contributions, because all of the assets could be on pair, on par. So they will be all the same. Right. That's risk area. Well, that's not the way that you see things in books, textbooks. Right? But there's some other method, some other methodology that we could use to choose weights. Alright? Well, in this you can solve like so. Alright? Or you can change it somehow a little bit, somehow so the numerator is attractable, but that is sort of the bottom line when it comes to the calculating the rates. Alright? So here below the, so I will not be able to do this for you, but I will tell you where to find the function. Here, okay? This is good, enough? Okay. Well, because I will not ask questions on risk parity in the exam, but just for you to sort of explore with your whole master in finance skills, you should be interested in this stuff. Yeah. So just tell you how to do that and leave it for you as an example. So here, well, actually, this guy has all of these basically risk functions, the plots, how the parameters are estimated, what are the portfolio models, and so on and so forth. So let's look at the portfolio models, all right, that we have here. So what type of portfolio models are there? There are very many, all right? So, well, I mean, sort of you have some risk measure or something that you start to indeed maximize with respect to some constraints and so on and so forth. So they are very big ones, all right? So these are the mean variance or some theories. So tell you what are the functions. They are all very well defined and documented, so you can read them. But let's maybe look at the examples. And then there is risk parity models. Right? There's also Black-Little map. That is also a fun one. So let's look at the risk parity models. Right? There are many, essentially, that this guy has done. 1, 2, 3, 4, 5, 6, 7. There are all of those. And then they are sort of different in terms of how the implementation was done. This one that I just explained is the vanilla, or the simplest form of risk parity. Alright. That is the first. Right, so the first basically stuff. Maybe let's take a look and then see what is in there. Alright, so hopefully it will still work. Alright. So that's a very simple tutorial. So he has some assets, sorts them, gets the data. Right? Well, these codes are too old. They will not work. You can't get them working. Because he uses Yahoo Finance, and Yahoo doesn't provide free data anymore as of the beginning of this year. So you need some other sources of data. Maybe Bloomberg, maybe some other. You have sources of data? No? You don't have free data. So you have to buy them. But I give you a lot of data. 10 years of components of S&P 500 and the NYSE components, daily and monthly. And I think there is also DAX components, the DAX effect. So you have them daily, monthly, so you can use them, play around with them for your own sake. Okay? But this guy uses download, which doesn't work anymore. So maybe let's go through and this exercise. So it basically has the data in so in percentages, then it has the risk folio, passes the returns the way we were doing it. Estimates the mean and variance component is using historical data. Alright. So first, well, I mean that is what we have. That is the risk measure meters, but that's sharp. Risk-free rate sets to 0. That is the utility function, which is not relevant here, right? And then gets the dates. That's somehow very simple. And gets a, these are what we did, right? So pretty much. Right? So that's what we have. And then, well, I mean, that is the standard sharp model, so without risk parity. And then when there is a function which calculates the risk, I think this function doesn't work, but that doesn't matter. You can always calculate it like this. So remember, maybe you take a note of that. Or if you forgot, then you take a derivative for God's sake, and that's not a problem. Right? So you can have it. And then program it. Alright, so that's not a big deal. And to calculate the risk contribution, so for this standard model, alright, so without risk parity, then his assets have different risk contributions. Right? Some have more than half of it, I don't know what is that, so that's sort of what we do with the red line. So some have more, some have less. So that is the point of this graph. Right? And then, well, let's look at the risk parity. Right? So here then we have a function which is the, so the rates that we get not optimized, but it is called RP optimization. That's a risk parity optimization. That's a little different. Well, I mean here, one can also put bounds on the risk contribution here. This is none. It means there is no constraint, right? And then once you do that, then you get some base. Right? So that does the optimization for us. Right? The optimization is not based on any utility. There is no utility involved, but it is actually based on choosing the rates in such a way that the risk contribution across all of the assets is the same. There is no utility. That's different. Okay. And then if you do this, then there will be some other rating scheme, of course, that comes out, and then you get the total value. Right? So the risk contribution of all of the assets becomes the same. Right? So whether this approach, risk parity, is better than the sharp maximization, I don't know. It matters for you, so you can just check and then see which one does bring more returns with less risk. Okay? If one of these approaches brings more return and less use, then that is the one that you should take, because that brings more money. Sort of in general. So that's sort of something maybe new that I mean new on top of the theory that you have. Alright? Well again, I just want to tell you that this is not optimizing or maximizing the utility function. It heads for getting the weights, the risk contributions equal across all of the assets. Risk mix becomes, well, it makes sense to do because you may taper indeed the contribution of, say, Amazon. It's nice to have Amazon because it has big returns. It's nice to have NVIDIA, but they are problematic, they are risky. You may invest in them and lose over a period of time. And maybe, well, a long-term earn, but some other something that, well, this guy indeed helps us with. To sort of tapers them, puts some bounds on the contribution of the risk, so that the risk distribution is more even. And so on and so forth. That's sort of a very nice exercise. But there are more examples, and there are more models, and you would not finish them, finish learning them properly soon, right? Because there are so many. But that's nice, and that's nice to basically have them. I don't know all of them. Some I know, right? I've played around with. Some I know less. Alright, so these are nice examples. As I said, they don't work, all of them, because the data are not really relevant. And then you may, that's open source now, and then you may change the functions so that they work more their own way. I think that's enough. Yeah. So what I want actually to do now is to ask you if you have questions.
Let's go back and digest first.
Sorry?
Let's just go back and digest first.
Yeah, sure. You need some time. Well, apart from that, I thank you very much for being there and supporting us. And thank you all for asking questions and making it fun today. Though it was, I mean, oftentimes it's very dry, this class, right? Somehow numbers, and you have something, some curve, and then you have to make sense of it. But it's also fun.